Okay, we want to continue our synthesis of aspirin discussion, and I want to take a look at the mechanisms. There are a couple of different reactions we can look at, and they're all examples of nucleophilic acyl substitution reactions. So let's look at the mechanism for the synthesis of aspirin itself. So this is our acetic anhydride, and this is our acid catalyst. So that's from our catalyst. And what happens is you protonate one of the carbonyl oxygens. And why do we do this? This makes a better electrophile. So this carbon right here of the carbonyl is an electrophilic carbon, and nucleophile is going to attack that. And by protonating the oxygen, it makes it a better electrophile. So our nucleophile is the salicylic acid, and it's the phenol oxygen that attacks the electrophile, kicks these electrons up. Now what happens is this hydrogen has to go. The oxygen should only have 2 bonds and 2 lone pairs, and in the product, aspirin, that hydrogen is not there. So you see that this oxygen takes that hydrogen and it moves over there like so, as you see in the product here. And now we've formed our leaving group. We're going to lose acetic acid as a leaving group. In the next step, the leaving group departs, and this occurs by a lone pair on the oxygen reforming the pi bond to reestablish the carbonyl, and this bond breaks, and so acetic acid departs as a leaving group. And here is that new pi bond. We've reestablished the carbonyl. There's our carbonyl reestablished, but we still have hydrogen and that oxygen, which has to go in the next step. And so this bond becomes a lone pair again, and we lose H+. Remember, that was a catalyst. So a lot of times we just show H+ hopping on and off things. Probably something takes it, like water. Water might come in and grab that, becomes H3O+. So that was a lot to take in, but I just want to show you the generalized scheme, okay? Of course, during this mechanism, we protonate to make a better electrophile. Then the nucleophile attacks, H+ hops on and off of things, eventually leading to a good leaving group, and the leaving group departs. But if you ignore H+ and what it's doing and look at everything else, this is basically what is happening. Our nucleophile attacks the electrophilic carbon of the carbonyl. These electrons go up onto the oxygen. Eventually, these electrons come back down and reform the pi bond. Now, I should say all of these steps are in equilibrium. When these electrons come down, the nucleophile that just added in could get kicked off when we go back to starting material. But another thing could happen. This bond, instead of the nucleophile coming back off, this group that's already on at the beginning could come off. And that's what happens here. We've got our leaving group that comes off. And that's the basic mechanism. So a nucleophile attacks the carbonyl, electrons get kicked up onto the oxygen, pi bond electrons do. They come back down to reestablish the pi bond, and the leaving group gets kicked off. So that's the general mechanism. We just saw this generalized mechanism. Let me just do that generalized mechanism. Here. Nucleophile attacks, electrons get kicked up, they come back down, and the leaving group departs. Of course, H plus hops on and off of things, but you get the picture. Now this is bonded to the carbonyl carbon, and we get acetic acid. Notice that you could do this with a similar nucleophile, water. Water could attack. Electrons get kicked up, they come down, this group departs. Again, H plus hops on and off of things. But what do we have here? We would have on one side that, but we would also have the leaving group. So we actually get two acetic acid molecules. This is the reaction that we do when we quench at the end. We add water, there's still the acid catalyst around, and any extra acetic anhydride reacts with the water and gets destroyed. By the way, you can have aspirin be attacked by water. Here is our ester, right? There's our ester. If you look at this as being the electrophilic carbon, and this is the leaving group, you could think of water attacking the carbonyl. These electrons go up, they come back down, and the leaving group departs. And we get back to salicylic acid and acetic acid. So please note, this is not the reverse of the synthesis. Our synthesis is salicylic acid and acetic anhydride. This is not the reverse. We're not going back to salicylic acid and acetic anhydride. We're going to salicylic acid and acetic acid. So this can happen slowly, like if aspirin's sitting around and some moisture gets in it. It'll happen a lot faster with an acid catalyst because that makes the electrophile stronger, so the reaction goes faster. But it can still happen over time if aspirin has moisture in it. And when this does happen, your aspirin might start to smell like vinegar, because vinegar is a solution of acetic acid. And when your aspirin breaks down, you produce this as one of the products, and that's what you smell, is that vinegar smell.